Treatment with phosphorus pentachloride gives N-methylbenjamide C. So A is over here, this gives C. So we get this C from this. So this is N-methylbenjamide, N methylbenjamide, um, and from B we get N-phenylacetamide. So this is N-phenylacetamide, uh, which is in the Beckmann rearrangement. So I'm not going to talk about the Beckmann rearrangement. The identification of C and D tells us that the rearrangement involves a transmigration with respect to the hydroxyl group of the oxime. So it is something like this. Say like we have this thing CH3 C double bond. So I make it as pH, and this becomes NOH. So the medium is acidic, so it becomes something like this. It goes off. So we have thing like CH3C double bond N plus, and it is over, pH is over here. Um, and So now what can happen is this CH3PH double bond N plus. So uh, this can migrate over here and this can migrate over here. So OH was over here. So if this migration takes place, then we call it as a trans, and if this, then it becomes cis. So let's see what they are saying is that it tells that the rearrangement involves a the identification of C and D. So we have this thing A gives this thing. So this can happen only when uh, uh, this can happen only when CH3 migrates, say like trans migration. So and this similarly in case of if we have this as a B. So if this migrates, this goes off, say like becoming like this, and this comes over here. So it again is a trans. So it tells that the migration is a trans. So that's how the products are letting us know the kind of a mechanism that is involved in a reaction. Let's move forward, and we have a determination of the presence of intermediates. So we have already known we already know how to uh, identify the products and what information we get out of it. But now we come to the determination of the presence of intermediates, and it says that one or more intermediates may be formed in a complex reaction. If transient, then they are detected by employing sophisticated physical methods. Otherwise, if they are stable, then they are isolated. So if they are stable, we are talking about intermediates, then it can be isolated. Sometimes intermediates are trapped by compound known as trapping agents. Sometimes intermediates are allowed to form normal products to get a hint of the reaction mechanism. Kinetic studies also provide formation of the intermediates in some cases. So first of all, we want to isolate the things. So sometimes intermediates are isolated before the reaction is completed by stopping the reaction or using the mild conditions. So we need to arrest the reaction, only then we can isolate it. And say like we take this example, isolation of three intermediates, 1, 2 and 3. 1, 2 and 3, they have been, so this is a Hoffman rearrangements. We all know what happens over there. It becomes something like R C double bond O N H B R, and then this goes off, and we have something like R C double bond O N. In fact, first of all, base uh, shall take away this one, so we have formation of this. Um, it goes like this. So it was already having um, one lone pair of electrons. So when it goes, so it becomes something like this, and now when this goes off, so it becomes R C double bond O N dot dot. This is a nitrene diradical. So isolation of intermediate 1, they have shown this one, that is what I was telling about. Then second, wherein the proton is taken away by base, and third is this. So we have a nitrene formation over here. So what happens is then is like this. Uh, Now what happens? This is 6 electron system, electron deficient. So this is going to migrate over here. So how it migrates? It migrates in such a way that this becomes minus and then it becomes plus. So this migrates over here. So it becomes something like this, C double bond O plus, and we have N dot dot and R, right? And then OH minus, say from water can come, and then we have RNH COH. So but in between we also so we are having this thing RNC double bond O. So this can also be written like this thing. uh, this thing can also be NC double bond O. This is plus and this is this and this, so we can always write it like this. So this becomes CO double bond N dot R, RNCO. And when we compare it with this one, so this is the same. So what they are saying is that 1, 2 and 3 intermediates have been isolated during the formation of primary amine from an amide by Hofmann rearrangement, accounts for the formation of these intermediates during the course of reaction. Similarly, there is a one reaction in which neighbor rearrangement takes place. Intermediate fourth uh, has been isolated, accounting for the formation of such kinds of intermediates. So we can have many other examples. Here we know about Meisenheimer complex, uh, the formation of the cyclohexadienylide anion during a bimolecular aromatic nucleophilic substitution is substantiated by the formation of fourths. So this is a nucleophilic substitution, aromatic nucleophilic substitution. So this goes over here, addition takes place. So it's like well, it has been drawn like this, but we can draw it like this, and nucleophile goes over here, so it goes over here and this becomes this. So then it becomes like this minus, and we have this thing sigma complex. And now uh, since uh, it was one hydrogen and this is again a one hydrogen, so in order to get back its aromaticity, it would like to go like to form a double bond, and X minus goes like this. So we have H plus and X minus, but this is taking very fast. So this is Meisenheimer complex, sigma complex. Similarly, we have this nitro trinitro compound. So the base comes, and base is now acting more like a nucleophile, uh, kinetically controlled reaction. So it comes over here, right? And we have a minus, as we discussed the mechanism over here. So we have a minus over here, this thing. And similarly, if we had taken OC2H5, so the intermediate 5 would have been the same. So this tells that the proof of the formation of cyclohexadienylide anion during bimolecular aromatic nuclear substitution is substantiated by the formation of fourth. Okay, so moving forward, this reaction, bimolecular aromatic electrophilic substitution. So uh, we all know that this is an electrophile, so it will be attracted by benzene, and the benzene will have a plus ion carbocation formation taking place, and eventually this the substitution takes place. I mean, one of the hydrogen, this hydrogen goes away because it wants to get back to its aromaticity. So the next thing that comes is the detection of intermediates, how we are going to detect uh, these intermediates. So the first is physical methods of detecting intermediates. Now the thing is that intermediates are unstable because we all know that we have a reactant, intermediates and their products. So transition states is very unstable, but intermediates, as we talked about just now, we can have intermediates where we can isolate them if possible, otherwise they're unstable. So they're often determined by the physical methods. So we employ a lot of spectroscopic techniques, IR, UV visible, NMR and CIDMP, and then the flash photolysis employed to study transient intermediates in solid, liquid and gaseous state. So we can trap the reaction intermediates. So we can trap the reaction uh, intermediates, say like we have this carbocation formation taking place uh, in when a bromine molecule comes in front of this. So we all know this becomes Br plus and Br minus. So that induces uh, changes in it, and a carbocation formation takes place over here. Now Br minus can come over here. So we have this formation in place of Br minus. If we have OH minus, Cn minus, or say uh, nitrite, we can have this all. So in a way, we are using all these anion to trap this C plus. Similarly, we can trap free radicals.